Imagine a robot navigating a cluttered kitchen. It sees a mug on the counter, a bowl on the floor, and a knife on the table. It needs to know where each object is, not just what it is, to pick up the knife without knocking over the bowl. But here's the problem. Most large vision language models, the AI systems behind tools like ChatGPT, QN, and others, are terrible at spatial reasoning. They can describe what's in an image, but they struggle to understand where things are in 3D space, how far apart they are, or which direction they're facing. This isn't just a minor flaw. It's a fundamental bottleneck for real-world applications, autonomous driving, robotic manipulation, embodied AI, where understanding the physical world is everything. Today, we dive into a breakthrough paper from the Shanghai AI Lab and collaborators. Spatial SSRL, a new self-supervised reinforcement learning paradigm that dramatically improves spatial understanding in large vision language models, without human labels, expensive tools, or synthetic environments. Let's break it down. The core problem: why LVLMs fail at spatial reasoning. Despite near saturation on tasks like image captioning, object detection, and visual question answering, LVLMs still lag behind humans in spatial reasoning. Why? Because most training pipelines rely on extrinsic supervision, expensive human annotations, proprietary depth estimation tools, or synthetic 3D environments. These methods are costly, hard to scale, and often don't generalize well to real-world images. Even recent advances using reinforcement learning with verifiable rewards are limited. They work only in constrained 3D scan environments, requiring complex pipelines and specialized assets. So the open challenge has been, can we scale verifiable, high-quality spatial supervision to ordinary RGB or RGB-D images, without any human or model-generated labels? The answer is yes, and it comes from a clever idea: use the image itself as the teacher. Introducing Spatial SSRL, self-supervised reinforcement learning. Spatial SSRL is a paradigm shift. Instead of relying on external annotations, it extracts intrinsic supervision signals directly from the structure of the image, using 5 self-supervised pretext tasks. These tasks are designed to teach the model how to reason about space, not just memorize answers. And because the correct answers are deterministically verifiable from the image, they can be used as rewards in reinforcement learning, making this a true self-supervised RL framework. Let's walk through the 5 tasks. 1. Shuffled patch reordering. What's the original layout? You take an image, divide it into a grid of patches, shuffle them randomly, and ask, what was the original order? This forces the model to understand global 2D layout consistency, like how a table fits under a chair or how walls connect. It's not about edge matching, it's about holistic spatial coherence. To increase difficulty, one patch is masked with white, so the model can't cheat by just aligning borders. 2. Flipped patch recognition. Which patch is flipped? Randomly flip one patch vertically or horizontally and ask, which one? And how? This teaches the model to detect subtle orientation violations, like a mirror image of text, a face with reversed features, or a shadow pointing the wrong way. These are critical cues for understanding viewpoint and object orientation. 3. Cropped patch inpainting. What's the missing piece? Cut out a square region, zero it out, and give the model 4 options, 1 correct, 3 carefully crafted distractors. The distractors are a 90 degrees rotation of the real patch, an interior subregion, like a close-up of a detail, an exterior region, a larger context around the patch. This task demands fine-grained texture and structural reasoning, understanding how parts relate to the whole, which transfers to real-world scene understanding. 4. Regional depth ordering. Which region is closest to the camera? Using depth maps from RGB-D images, select 3 disjoint regions with increasing depth. Shuffle their labels, then ask, order them from closest to farthest. This teaches ordinal depth perception, a core skill for occlusion reasoning, 3D reconstruction, and depth estimation. The model must integrate depth cues, perspective, and spatial relationships, not just guess. 5. Relative 3D position prediction. From the object's perspective, where is the other object? Pick 2 points in the image. Assume an object is at one point with a known orientation, e.g., facing left. Then ask, from the object's viewpoint, is the second point to the left, right, front, or back? This is egocentric spatial reasoning, the kind needed for navigation, manipulation, and perspective taking. The model must perform a 2D rigid transformation, translate and rotate the second point into the object's local coordinate system. The answer depends on the signs of the transformed coordinates, a precise, mathematically verifiable output. Why this works: intrinsic, verifiable, scalable. Here's the genius: all ground truth answers are derived deterministically from the image structure. No human labels. No LLM annotations. No expensive tools. Zero human supervision. The model learns from the image itself. Tool-free scalability. Only raw RGB or RGB-D images are needed, collected from public datasets like COCO, Diode, and Megadepth. Natural verifiability. Each task has a binary or scalar reward, perfect for RL. The result: a dataset of 81,053 self-supervised QA pairs, called Spatial SSRL 81K, with 100% ground truth accuracy, because the answer is always right there in the image. Training, reinforcement learning with verifiable rewards. Now we fine-tune a base model, QN2, 5VL using Group Relative Policy Optimization, GRPO, a powerful RL algorithm. But here's a key trick, a cold start SFD phase. Why? Because the model starts with no idea how to format its reasoning. It fails to generate valid outputs, less than 5% success on complex tasks. So we first do a brief supervised fine-tuning on samples, just enough to teach the model how to respond. Then we switch to RL. The model is prompted to first think step by step within tags. Then put your final answer in \boxed. The reward function is two-part. Accuracy reward, 1 if the answer matches the deterministic ground truth, 0 otherwise. Format reward, 1 if the output follows the required structure, 0 otherwise. Final reward, R equals 0.9 times RAC plus 0.1 times RFMT. We weight accuracy higher because format compliance stabilizes quickly, while accuracy improvements require full RL training. Results, a game-changing leap in spatial reasoning. On 7 diverse spatial benchmarks, including Spatial 457, 3DSR bench, VSI bench, and up, Spatial SSRL delivers consistent, significant gains. Spatial SSRL 3B, plus 463% average accuracy. Spatial SSRL 7B, plus 389% average accuracy. The largest jump, plus 867% on Spatial 457, a benchmark that demands complex pose estimation and multi-step reasoning. But here's the real win. The model doesn't just get better at spatial tasks, it gets better at everything. Even though the training was exclusively on spatial self-supervised tasks, the model preserves and even improves on general visual capabilities. On Bench, Halusian Bench, and Real-World QA, accuracy increases by plus 202% 3B and plus 057% 7B. On OCR and chart understanding, gains are plus 012% 3B and plus 122% 7B. Why? Because the pretext tasks require holistic scene understanding, global layout, texture continuity, fine-grained detail, which transfer to general vision. Ablation studies, what really works. When we train on individual tasks, we see clear patterns. Shuffled patch reordering excels at 2D layout and multi-step reasoning. Flipped patch recognition boosts logical and orientation reasoning. Cropped patch inpainting improves general visual comprehension. Regional depth ordering dominates 3D height understanding. Relative position prediction enhances general reasoning and multi-object relationships. But the real power comes from combination. The synergy between depth-free and depth-based tasks creates a model that understands both 2D structure and 3D geometry, and they reinforce each other. And here's a key insight. 2D tasks alone improve 3D reasoning, suggesting that strong 2D spatial understanding provides a powerful inductive bias for 3D inference. Why this matters, a new path to spatial intelligence. Spatial SSRL isn't just another fine-tuning trick. It's a new paradigm for training AI with spatial understanding. It's cost-effective, no human labels, no proprietary tools. Scalable, can be applied to any RGB or RGB-D image. Reproducible, fully end-to-end open source. Extensible, new tasks can be added without changing the pipeline. And it opens a new door, self-supervised learning as intrinsic reward for vision-language reasoning. This could be the key to building AI that doesn't just see the world, but truly understands it. Final thoughts. We've long known that vision-language models struggle with spatial reasoning. But the solution wasn't more data, more tools, or more complexity. It was simpler, use the image itself as the teacher. By designing tasks that exploit the inherent structure of images, their layout, depth, orientation, and consistency, Spatial SSRL teaches models to reason about space in a way that's verifiable, scalable, and generalizable. And the results? Not just better accuracy, but real spatial intelligence. This is a major step toward AI that can navigate, manipulate, and interact with the physical world, not just describe it. If you're interested in the code, model, or dataset, links are in the description. Check out the Spatial SSRL GitHub, Hugging Face model, and public dataset, all open for research and development. And if you found this helpful, hit like, subscribe, and share, because the future of AI isn't just smarter, it's spatially aware. Thanks for watching. See you in the next one.